hello, and welcome to the stream. Uh, since it turned out that I had a couple of hours in spare, I thought that I would just continue the tutorial series. Hopefully, I'll have enough time to do the pipeline state object and actually do some draw calls. We'll see, maybe not. It depends on how things goes. How things go. I'll just let the stream run here until we reach the scheduled starting point. And do some checkups here. As per usual, I will announce when I do the recording for the video series, and I'll try to fit in your comments and questions as we go along. But preferably at the end of each segment, so that the questions from the live chat potentially gets included in the video. There might be other people who will benefit from the questions. Of course, only questions related to the actual tutorial or the process of using DirectX 12 will be answered. I'll answer different questions in different ways. You could always join the Discord and ask questions there. I can't promise that I always have the time to answer all of them. Right now, there's not a lot of traffic, but there might be in the future, so yeah. Otherwise, you just leave a comment at the appropriate video if you want something further elaborated. Yeah, I'm just gonna hang out for a few minutes, and since the announcement of the stream was a bit late, I'll give people the chance to tune in. I'll also check out Twitch in case someone tunes in there, even though this is primarily a YouTube stream. I know it might be a bit early if you're living in the US. Yeah. Some parts of the US hasn't even awoken for the day yet. But yeah, I might as well spend the time talking a bit in case you're watching this in the future. So yeah, To sum up, last time we talked a bit about different memory allocations in terms of the GPU. We talked a bit about how to upload data. We created a simple version of a data upload in terms of the GPU. We checked out the debugging software in terms of NVIDIA Insight and rendered doc. So that was great. All right, just a couple of minutes more and I'll start doing this episode here. Last episode was a rather quick one. There are still improvements that we could do to our resource here. We could make a function that allows you to grab the underlying memory location in case it's CPU writable. You could even implement this part of the function on the actual resource itself and simply just store this pointer, and then whenever we deallocate or release the resource, then it would get unmapped. Since there are some CPU cycles related to actually mapping the resource, this could be a fairly efficient way of doing things. Yeah, let me just add a comment. So basically, all of this could be one big big method, except the unmap you would only do it in case of a release, and you would only do it if this pointer even was set. Okay, I think I might have been delaying the start of this enough, since I do have a bit of a time restriction in terms of today's stream. I won't be going as long as I sometimes do, since I need to go to do something later in the day. So I guess I have approximately 2.5 hours or something. I think we might be able to bang out a video about the actual pipeline stuff. Let's see. All right. I'll start the recording now. Let's see. Hello everyone, and welcome to this episode of our DirectX 12 beginner tutorial series, where we go through the process of building a DirectX 12 application from scratch in C++. Last episode we did some resource allocation on the GPU. We talked a bit about which kind of resource allocations were accessible by the CPU and which were mostly CPU, rather GPU sided. And I talked a bit about in the stream before this episode that actually this part of the method could be a part of the wrapper for each resource. You could store the pointer internally and only unmap when the resource gets released. But we will do that in the future. It's not that big of a change. Today I want to focus on the more what do you call it, intricate stuff of the DirectX 12 pipeline. It's a fundamental aspect of graphics programming that you might know from other languages, which include shaders, and a, it all revolves around how to do data processing on the GPU. We're going to talk about pipeline states and root signatures and shaders. So if we look up the DirectX 12 pipeline, you can see that there is a fine diagram here. We have our pipeline here, which has an input stage and an output stage. The pipeline is what generally happens to your data on the GPU. So it takes in usually vertex buffers and index buffers as a means of uploading data or storing data for the GPU to do operations on. Depending on your pipeline setup, the data will go through different data processing steps. It will always go through an input assembler, and usually it will go through a vertex shader. I say usually, I think it would happen almost always. The only thing I can think of where you don't necessarily use a vertex shader is if you have a entirely different setup than a graphics pipeline. Anyway, the data comes into the pipeline. It gets assembled as an input. It gets processed in the vertex shader, and then there are optional stages along the whole process. We could along the way do vertex processing and simply output the data without doing any further calculations, or it could be passed along the pipeline if you have the stages for it to do rasterization and pixel shading and then some output merging. The output merging is bidirectionally linked to the render target and the depth stencil. The render target is what we saw during a previous episode where we simply link whatever output we have to something in the swap chain, a resource in the swap chain, and we can output that and eventually present it to the screen. We can also write to a depth and stencil buffer. These are two separate objects. The depth buffer is a buffer that contains the depth of each pixel that you have computed in your pixel shader. It also controls whether you could overwrite that certain pixel. You could only overwrite that if the pixel in pixel was closer to the screen slash camera than the existing pixel. The thing is that we usually have information up here that is in 3D space, at least for 3D graphics. It might be in 2D space, then nothing really changes in that regard. But down here we will always have a, or I say always, not necessarily, but usually we would have a 2D space output with a 3D component in terms of the depth. This means that a certain transformation goes on, and yeah, the depth itself gets kind of like split off into a separate buffer where it's used to handle draw calls and object overlaps. Yeah, there are different custom shaders that do different things. I think it's out of this scope, at least for now, to talk a bit about those different shaders. We might revisit it in the future. But you might be wondering, well, if I only input vertices or indices for those vertices into the pipeline, how do I use a texture? How do I do different mathematical operations? And each pipeline has sort of an input layout that is related to not only the vertices or indices, but also a separate input layout that relates to other data structures. So you can, in those input slots, which is called root arguments, define several other resources that should be available to the pipeline at different stages to do its computations. You could have constants that you want to be defined for a specific pipeline. You could have descriptors, meaning that you could have certain buffers that were already defined as an argument for this pipeline. Usually that is called something like constant buffers, structured buffers, fixed byte arrays, or whatever we want to call them. In Vulkan, they are probably called uniforms, if I remember correctly. So yeah, we could define that as an input to the pipeline. We could also define tables of several resources stemming from a descriptor heap. We saw a descriptor heap in terms of the swap chain, where the swap chain had its render target view descriptor heap. It was basically a table over references to the render target views with CPU and actually GPU addresses. We only needed the CPU addresses, so therefore we only use those. But you could also do other resources allocated by to tables in terms of their addresses in memory. For instance, you could do shader resource views. That is usually something that is defined as a resource that the shader uses. It could be a texture. It could be a 3D texture. It could be basically a lot of things. It could also be an output from another part of a pipeline or a previous pipeline state. It could also be a series of constant buffers. Constant buffers are basically buffers of numbers, information that you want to use in your pipeline. But constant buffers are buffers that are optimized for very rapid computations. So you could define a lot of different buffers and put their memory address in a table, which would reside in a heap, also called a descriptor heap. So you could bind all these things to a pipeline besides the vertices and indices. You can actually also bind so-called static samplers. They handle texture sampling and help the pixel shader out in terms of which pixels to draw. Maybe you want to draw a texture on a certain object after it has been rasterized or changed into 2D screen space. And these samplers help you do that. They also handle upsampling and downsampling and so forth. Static samplers are basically a predefined set of samplers that are available to the whole pipeline. Yeah. So, as I've mentioned, we do not only need the buffers themselves with the vertices and indices, we also need some kind of input description in terms of what other data structures are supposed to flow into this pipeline and handle control of those. So we need to create two input specifications. We also need to define the actual pipeline itself. What is it supposed to do? And then there is even more to it. You can see here a compute pipeline is differently structured. It doesn't have any of these stages here. But actually, these parts of the pipeline, those that are defined as shader stages, and not fixed function units, but either teal or light blue, maybe light teal color, are all shader programs, which means that they are programmable. Who would have thought, right? So we can't just create the pipeline and set up its inputs. We also need to do some programs that handle the behavior of each of these shaders. We will only do the vertex shader and the pixel shader since it's not needed to do the other shaders for basic rendering. But of course, there are different functionality in the other stages. So yeah, excuse me. You could use them down the line. So right now we have an outline that is related to what we want to do in this episode. Hopefully we will get done doing it all, but we will see. We want to create shader programs. We want to set up two input layouts, one for vertex index buffers +1 for data structures needed for the pipeline, and actually for specific use inside our shader programs. And then we need to set up the actual pipeline. Hello and welcome. We will do one series of pipeline. Many advanced renderers will have several pipelines and do several different things during one frame, but yeah, we will do everything related to the pipeline, I hope, during the episode before I have to go. So that's the overall plan. So I just talked for maybe, let's see, 15 minutes about what we're gonna do today. And we will basically create shader programs, set up our two input layouts. One is called the root signature and one is called the specific input layout for the pipeline. And then we will set up an actual pipeline. And then hopefully we will be able to do a draw call. So we will create a wrapper for the shaders and their compilations. As any other program, you need to do compilations in terms of actually being able to use the program. It has to be turned into bytecode that can be run on the GPU. And we will create the actual shaders / programs themselves. And down here, we will do the pipeline input state. And we would do the root signature. And here we will simply set parameters and bind everything together. We will, of course, create a wrapper, which will set the parameters and then create the functionality that couples everything into a complete pipeline. We will see if I will be able to make the actual draw calls today. Hopefully, we will be able to. It would be nice if it were to pan out that way. I think I'll segment this as a separate video and start on the actual code in terms of the shader, which we will start doing. In the next episode. So I'll end the video here. I'll um, yeah, be doing more code in the next video. Hopefully I explained a bit about the graphics pipeline itself so that it makes sort of sense what we're trying to do. All right, hopefully I'll see you in the next episode. Let's see. Okay, and here on the stream, I will just restart the recording. Since I only did its explanation in the last recording, so yeah, I'll start the new recording here when we do the actual code. Alright, hi and welcome to this next episode in our tutorial series on doing a DirectX application from scratch. In the last episode, I talked a bit about how the pipeline state itself was set up, or rather the pipeline on the in terms of doing rendering was set up, what we need to do a pipeline, and basically what is a prerequisite for doing draw calls. In this episode, we will start creating the actual shader programs and the wrapper for the shader. Maybe I'll wait with the, no, I'll do a basic shader program since it's not many lines of code. So we will create the wrapper for our shaders. And since shaders are a part of a pipeline, we will simply create a folder for that. We will create an HLSL shader. HLSL is the Microsoft shader language, which DirectX 12 uses, so it makes sense to call our shaders that. We will, of course, create our namespace. And let's see, I don't think we want a wrapper for the first time in our whole series. We do not have a DirectX interface. We are creating our own wrapper here, which we will allow our system to default construct, meaning that it can be empty. We, of course, need to do this public. We could also do an destruct, but I can't remember whether it's needed. We want to initialize, excuse me, our shader program, and when we initialize it, we want to do compilations. We will take a long pointer to a wide string in terms of the file name, since we will be working with files. Since we can do different shader programs, as you see here, it is also preferable that we create a sort of enum class maybe related to our actual shader itself. So let's do an enum shader type, and we will do vertex pixel shaders here. And this will also take a const shader type. And, oh, I forgot the namespace. I'm about to go insane. All right, so our shader will take a file name and a shader type. We will implement more functionality in just a bit. This will take a series of flags, which are all uints. Shader compilation, DirectX 12. Compile. And we need to call this function here, compile from file. We can look up the different, we need the file name, we need some macros. We don't dive into macros today. We could do an include file. We need an entry point. We need a compilation target, and then we can set some flags. Let's see. We can do compilation debug. We like that since we're not really done with our application. These are not production flags, of course, but we would like them anyway. You could do different builds in terms of, excuse me, different compilations of your program here. Okay, I think we also need a header file. Let's see, what does the documentation say? To compile this, we need to use this function, which is stored in, do we have a library specification? Yeah, D3D compiler. That is why our macros there do not register. So we, let's see, want to include that. We want a D3D compiler, and I know that this also needs a lib, so we will be adding our D3D compiler.lib, which it also states here. Let's see. So we need that. Now our flag does register. We can go back to our flag lists. We don't want optimization since we're still debugging, and we want output in terms of whether our application really compiles. Let's see. You can change the data set in terms of how matrices are stored. Optimization levels. You can actually specify warnings are errors, and we want some clean, nice shader program code. So I think we are going to use that flag. It will mean that the shader will not compile even if we only get a warning. We want to make sure that our resources are bound in terms of compilation. That's also in terms of referencing in the actual shader programs and the pipeline itself. And do we want any other flags? I'm not sure that we want any other flags. Let's see. No, I think we're actually good here. Great stuff. All right. So, as I've mentioned, we will compile a shader program into bytecode. We want some error outputs here in terms of the actual compilation. You can see that this method here returns and one of the return codes. Well, there are different return codes. One of them is okay if everything went fine. So this corresponds to our H result. And we will simply, I can't spell, store the result of this operation here in an H result, and then we can do some handling of that error. As I've mentioned, we will not be doing macros. We can simply do a 0 here. The include pointer here can be set, but an optional pointer to an include interface, blah blah blah. If you set it to 0 and the shader contains an include file, you will get a compile error. We can instead pass this macro, which is a pointer to the default include handler. It includes files that are relative to the current directory, which is basically like we do our C++ includes. So we will use that macro. We need to specify an entry point. You can specify whatever you want, but like in C++, I actually like that our entry point is called main. Then we need to specify, let's see, our target platform. And you might ask, what on earth is a target platform? Well, there are different platforms here. I think we want the shader model, which is listed over here as 5.1, maybe. Yeah, let's see, feature support. It was listed here. Wiki, DirectX. If you remember in our previous episode, we can actually check, well, okay, we have actually shader model 6.0 support with our feature level of 12.1. Remember, this was the highest we could go in Windows 10. Windows 12, you can go feature model 12.2. Or if you have the Agility SDK, you can also do the feature level 12.2. But this means that we actually have access to our shader model 6.0. That would be pretty neat to use our shader model 6.0. We could do it like a let's see, it wants a pointer to a regular character array. So we could set our target here And let's see, and we need to set this const, and then actually we move it in here. We will do some operations in terms of figuring out which target we want, and then we will pass in our flags. We will pass in 0 as our secondary set of flags. You can do some other compilation options here. I have a child effect. I don't know anything about that. I've really never used it. And then we want to give it a pointer to the variable that receives a pointer to the blob interface that stores the actually compiled code. And then we can do the same thing for an error message. So what about our wrapper actually storing our bytecode? That would be pretty neat, I think. So therefore, let's create a member variable where we can well, is it just 3D blob? I think it might be. No? I just spelled it wrong. Whoops. ID 3D blob. Bytecode, and we will set that as 0. And we will simply give it the opportunity to use that. We will need to pass the address of that pointer so that we can store the actual pointer in that address. And then we would also like for it to be able to pass out a error message. So we will also give it the error message in case we do get a compilation error. All right. We do some manual error handling here. If the result is unlike SOK, we simply print out the shader loading error was, and then we pass out the error code. We do not do any specific parsing of it. You could do that if you wanted to, but yeah, I'm gonna skip that. Next, we want to ask our system if we didn't run into a problem here. Maybe we want some information about the error message if there were one. If this pointer is set, there's an error message, and we will print out the shader compilation error. And we will use our error message here where we will get the pointer to the underlying buffer. It's just a data structure. So we're actually kind of free to interpret this as we want. Let's see, do we have any other methods? Yeah, we can release it, we can get the size of it, and we can ask if it can be cast as a different interface if we wanted to, but we will simply get the buffer pointer. And since it's an error message, we might hope that it's able to be parsed out as a series of characters. Let's hope that. I'm unsure whether these values up here are actually able to be parsed out as a series of uh, um, characters. We could test it. I really have no idea. But what if we cast the information as const char pointers? This means that we could simply pass it out as information here. I think this would result in, if it only were numbers, that we probably either would get a series of numbers or would end up in a situation where we would simply just get some nonsense printed out. But anyway, we could print out our information here. We loaded the shader, and we simply pass in our file name here, and we tell that we successfully compiled something here. If we get an error message right now, we could return so that we do not print that out in case we didn't succeed in actually loading the shader. We would, since we created this object here, and since it might be allocated, this will go out of scope. So I think it will be deallocated since it's not referenced anymore. Yeah, I think so. I don't actually know about the interface, whether it succeeds in successfully resetting. But let's see, if we have a bytecode pointer here, well, it's already possible to set that as a null pointer. So we can check on it being 0. If it's not 0, we simply want to release this. Whenever we destroy a shader, we of course want to call release as per default. Let's see. All right, this is basically our shader wrapper. Which is great stuff. We now have a no, we forgot something. I still need to tell the program actually what kind of target output that we want to compile towards, and we will ask for the shader type here. If it's a vertex shader, we will set our target here to be our vertex shader 6.0. Is it that terminology? Let me see. I think so. Let's see. PS. Yeah, let's try compiling to 6.0. And we of course need a break here and a semicolon there. Otherwise, we will need to whoops. We want to compile a pixel shader, and then the target will be, of course, pixel shader 6.0. And we need a break here. Okay. If we do not have any of these cases, we would like to not break, but actually return here. Not case, just default. And we would like to print an error unsupported shader target. Compilation target. All right. Let's test this out. Also, you will get a feel for the actual debugger in terms of the shader. Let's see. We could create a shader. Let's include this for testing in here. Pipeline shader. Test shader. And we can create an empty one, and we will initialize it. And let's create a directory that is called shader, vertex shader, HLSL, and then we of course want the HLSL shader type of the vertex shader. Let's try that. And this needs to be a literal because it's a wide character array. This will not compile because yeah, you can even see that we have a problem in terms of handling the memory location. But as you can see here, we have an shader loading error, which is actually here. And of course, we have a loading error, and we couldn't cast it to a const char pointer, so that doesn't make any sense. Let's remove that. We didn't get any output. But yeah, that is of course because we haven't created a shader. And since we precompile a DLL that is used inside our application, that means that this is actually the application, and every um, part of the lookups that the engine does is actually relative to the application itself. So that means that we don't need to create shaders in our engine. We want to create it in our application, which is pretty fine if in case you're doing a game that runs on a engine DLL. That means that you can specify um, shaders relative to the game directory, and yeah, you don't have to fiddle around with subfolders of the engine and so forth. So let's see, I can't spell this right, so I think I need an S on this. Yeah, shade does. And we want to create a vertex shader.hlsl. Actually, since it's a Microsoft programming language, Visual Studio recognizes those. We don't care about the actual type we choose here. Let's just do a vertex shader.hlsl. And it immediately creates a method here, which is the standard entry point for a method here in terms of shader programming. Remember, here we actually specified an entry point, so if you chose some other entry point than main, you would have to write another function here. Let's just see if our program here actually gets found by our shader compilation algorithm. Let's see, we don't want to compile this, so we exclude it from the project, even though we can open it. Let's see. Whoops. Shader loading error was blah blah blah. And maybe we want to look that up. But we also get a shader compilation error. Well, that's peculiar. Maybe this value that we get actually is the same as a compilation error. Let's see. Let's see. A return code. Maybe we want to translate this return code here. Let's do a calculator and then switch this to a programmer. Then we can type in the hexadecimal number. We get a flag that is 8876. 88777. DXTI error codes. Let's look it up. Do we find anything that resembles this? Nope. Anyway, it might simply be a compilation error code, so we in reality get both these. Okay. It doesn't recognize the compiler target, So that either means that, let's see, we wrote in the wrong target, or maybe our feature level doesn't really support it, or uh, maybe this compiler doesn't. Maybe these are newer actually. No. Anyway, vertex shader, pixel shader. Well, let's see if it complains if I revert back to 5.1. Usually that's a failsafe. 5.1 here. Let's try that. Yeah, now it complains that there are no main entry point. So our feature level might not support 6.0. I'll have to look into that. I don't know if it's the compilation method or it's let's see, DirectX compile shader 6.0 HSL. Okay, so we need a DirectX shader compiler that can compile programs that are higher. Okay, so that's the problem that we ran into. The compiler itself, the method, doesn't support shader model 6.0, even though our feature level does. So we need to find a way to compile that if we want to use it. Let's see. Yeah. Yeah. 6.0. For shader model 6, you use here. Okay. You can always look up that it seems like a standalone program. You would probably just have to load the bytecode afterwards. Okay. You can always look into that. We will just use 5.1 for now. We aren't doing ray tracing anyway in this series, so we don't need to upgrade to 6.0 or 6.1 yet. But yeah, at least you know now that in terms of shader model 6, you need to use the standalone program that Microsoft provides here on this GitHub repo. Okay, but no problem. We got our code running by downgrading to an earlier version. 5.1 is pretty fine as long as you're not doing ray tracing. And as you can see here, there's still an error in terms of the loading. I'm not sure whether it's the same. No, it changed. So it's a different loading error. It was, remember, it's just parsing out that we weren't getting the SOK, meaning that something failed. But we now do get a different compilation error. Main entry point was not found. And if you were awake when I did this, you see that I actually commented out the entry point. Now that we have an entry point, we basically have a shader program, and you can see here we successfully loaded the shader program. Right now it doesn't do anything, but we compiled a shader program with an entry point that, although it doesn't do anything, is actually successfully compiled and stored inside the bytecode. Great stuff. that is basically it in terms of getting set up with shaders. Of course, we're not done at all with shaders, but we had a goal that was to create a wrapper for shaders and their compilation, which we've done. And then we need to create the actual shader program. We will return to that later because it makes more sense when we can see the whole pipeline kind of like doing its thing. So now I'll be taking questions if there are any. And if there aren't any questions, I'll round off this part of the video series, and then I will do a half a minute, maybe a minute break, and I will continue on the series. Next, we will do the root signature, since we can't really create a pipeline without a root signature. And we might contemplate how to do these things. We could do a wrapper. It's faster to just set it up without a wrapper, but it's usually somewhat of a hassle to manage your input states by hand, but we could do it. We will leave that as a question mark, and we will decide whenever we get to the actual pipeline implementation. Okay. It doesn't seem that there are any questions, so we should probably just create the wrapper for the root signature. Yeah, okay, I'll end the recording here. And I'll just upload the videos in terms of YouTube. Before we continue on, that would also mean that we have a small break here. Let's see. Let's see. Let me just set this up. There we go. And let me set up this next one, and of course update the GitHub repo. Let's see. We got to 12. Creating a HTML shader wrapper. And let's see. Okay, I'm almost done here. There we go. And we need to 11, 12, episode 12, creating a shader wrapper. Let's see. Did we? Okay, I think we did it. Let me just check the repo here. Yeah, we updated that now. And we successfully created the all right. Let's close that. Great stuff. Okay. Maybe we should just get going on the next part so that we don't end up in lack of time. Hello and welcome to the next part of this video tutorial series on how to create your first DirectX 12 application in C++ from scratch. During our previous episodes, we started the process of creating the whole graphics pipeline outlined in episode 11. During our last episode, we got done with the wrapper for the shaders and their compilations. We created a shader which contains nothing. Next, we want another prerequisite for the whole pipeline in terms of rendering. And let me just close some of this. We don't need that for now. We will be doing the root signature. I was contemplating whether we need a wrapper for the actual input state slash input layout. It's actually called layout in DirectX 12. Yeah, but we'll see what we think makes the most sense. We will create a wrapper for our root signature, and we will discuss that more in detail. We will make sure that we have our namespaces set up. There we go. And of course, in our CPP file, we want to do the same so that we don't go insane. All right. A root signature is something that, as many other DirectX related API calls, does have uh, a um, interface. That was the word I was looking for. So we want a ID 3D12 root signature interface. We want to be able to create a root signature that is a simple and nice root signature, which will basically be a root empty root signature here. We of course want our mandatory release function, and then we also want a destructor here. Let's implement all of these methods. Let's see, our destructor should call our release function. Our release function should check if we can actually access our compiler, if it has anything assigned rather. And our excuse me, our well, maybe we don't want a default constructor because, or rather, maybe we don't want to specify the default constructor because actually, how do we create a root signature? DirectX 12. Well, let's see. Creating a root signature. Blah blah blah. We need to specify some information, serialization, create root signature. So we need our device. This means that we would rather initialize it afterwards, at least how we do things in our program here. Pointer to the device. So now we can create an empty root signature, which is basically not empty, but it's just containing not anything. Well, our create root signature function takes in a blob with the root signature and somewhere to store it. But maybe we find that to be somewhat bothersome. Maybe we can use this serialized root signature since it basically just stores it in a blob instead. Maybe that makes more sense. Let's see. Do we like that? Well, okay. Generally, this says that this creates a root signature of a specific type, version 1.0. It has been superseded, which means that we can create any version. What's the difference between the versions? Well, root signature version, blah, blah, blah. Okay, we can do more elaborate instructions in terms of descriptor heaps. We won't be bothering with that, so we will just use our old root signature that will probably be fine. In any case, we want to, let's see, call this function to serialize a root signature that we can pass along to our create root signature method. So in our create root signature method on our device, we don't need a node mask. We need our blob with the serialized root signature. We need the length of the blob, and then we want to store our API pointer on somewhere. That somewhere will be our com pointer, underlying pointer here. So I think we should start with actually doing the serialized root signature, and that takes a version root signature description, which is this struct here. So we will fill out that root signature description here, and we will see if we can initialize it as 0. That we can. We will do a version 1.0 since we don't want to mess around with the different setups of the descriptor heaps. That's a more advanced topic and optimization based, so we don't care about that. We are only doing a simple application for now. So, well, this contains a union that contains this struct here. It wants a number of parameters in the root signature. Remember what I talked about in the overview episode. The root signature is sort of an input description in part on some components of the pipeline. So it takes a number of parameters. It also specifies a certain array which has a pointer that holds the actual parameters. As you can see here, you have to specify the number of static samplers and a pointer to the description of those static samplers. Then we need some flags. Let's see. As you can see here, if we plan on using an input assembler, which we do because we have input, we can specify a flag that, or rather, if we don't specify this flag, we can't access the input assembler. We can tell the pipeline that it's allowed to do certain stuff and not to allow certain stuff. It's basically related to the pipeline diagram that I showed you earlier. Yeah. So there are a lot of different options in terms of the root signature. We will get back to the root signature now. Okay. I think that we will actually, if we were only to do 2D rendering, we wouldn't actually need a root signature. But since I think that this tutorial series is probably a bit more interesting if we ever do 3D rendering, even though it's just simple 3D rendering, I think that we will actually show you, or rather I would show you how to set up a certain root parameter. We will create one root parameter with our standard root signature here. We could easily create a root signature that didn't have any parameters, and then it's just an empty root signature. But what would you get from that? Well, I don't think you would get anything out of it, and you would be no smarter in terms of handling root signatures and understanding what they actually do. So therefore, we will simply create a root signature with one parameter. And that parameter we will, in the future, use to do 3D rendering. So that is our sole purpose of our root signature here, to allow us to create one input. Let's see. We will put in one parameter, and we will have to create a parameter struct, a root parameter structure. And, oh, not num parameters. There we go. And we need to create our root parameter array, which will hold one parameter. And let's look up the structure here. It has a parameter type, which will be a constant buffer view, because we can put in constants, we can put in constant buffers, we can put in tables of different buffers and resources, or we could put in a shader resource view, which is usually a texture, or we could do an unordered access view, which is just data points, maybe outputs from different pipelines and so forth. We will do a constant buffer here. Let me copy this because I don't want to type it every time. As you can see, then there's a union in terms of a constant, a table, or a descriptor. We have chosen a view slash descriptor. So let's see, we need to specify a register space. Let's see, and we also need to specify a shader space. If you look up shader, HSL, register space, resource binding, you can see in this documentation that, let me see, do they have a nice image of it? No, they don't illustrate it graphically. Anyway, as you can see here, constant buffer views are stored in a shader register called B. Unordered access views are stored in a U register, and the SRVs are stored in a T register. The registers can be subdivided, so you can have parallel registers in so-called spaces, so space 0, space 1, and so forth. So that means that we register-wise would like the 0 register. We would also like the shader register to be 0, because we want this parameter to be stored in the first index for a constant buffer, meaning it will be stored at B0, T0 register space. And we don't need to specify the T0 unless we use it. So a constant buffer. Now we can put in the address of our parameter here. There we go. And we basically have our prerequisites, prerequisite requirements for our serialization of a root signature. So let's see. Now we want to call our, there we go, versioned serialize. Okay, and this returns an H result, as you might quickly have been able to grasp or see. Eval H result. We want to do this. It doesn't need a device. It's simply just a method that we pass in our root signature description. We give it a blob. So we need to define a blob. Pointer. Pointer to our serialized root signature. And as with the shader compilation, we would like an error blob just in case. You need debugging, so we pass it the serialized root signature and the pointer to the error blob. And then, of course, error serializing the root signature. There we go. And then, since we stored our root signature, we can create the root signature. Also, returning an H result, most of these functions do. So even though I didn't show you in the documentation, you can usually and then we ask how big is this, and then we want the IID, PPV, args. I always put in the H as if I'm shouting in pain, but I'm not shouting in pain. Error creating the root signature. There we go. We could do some error parsing if we wanted to. Maybe we want to, if the error blob actually is available, maybe we want to print wide character new. Isn't that the one that we used in the shader? Let's see. No, we actually just do like this. Let's just copy that. Only the, oh, I used a P here instead. Okay, whatever. All right. And that's it for our root signature. Let's test out this wrapper here. Maybe he will do some nice beats. Wah, wah, wah. Or better than she. I think that's more appropriate. Anyway, let's move on from that terrible joke. Let's do a root signature here. And we want to initialize it. And we want to give it our device. And let's see what happens. Does it compile? We have some kind of access violation. Problem serializing the root signature. Okay. So we might have some mistake here. Oh, I think we forgot something. Or rather, I forgot something. Not here. In here. We of course need to tell the root signature which version we're trying to compile. There we go. I think, well, we still do get an error. Okay, we also didn't specify a uh, shader visibility. We also forgot that in our root parameter. Yeah. Let's see. Good stuff that are um, compilation steps here do give us some error handling. Okay, I forgot those parameters. There we go. Everything got created successfully. Whoops. Um, root signature serialization error. There we go. Okay, that's our root signature. Our root signature currently has the layout that in the first slot of all the parameters in our root signature is reserved for a constant buffer view, meaning that we can simply store an address to our constant buffer, preferably on the GPU. It will be visible in our vertex shader, and it will get compiled with our generalized root signature. This is our standard root signature. You could do several different root signatures if you wanted to. They are stored in the COM pointer for the specific root signature, meaning that if you create separate pipelines, they would be able to hold different root signatures. Okay. Well, that is basically it for the root signature. I'll be doing questions if there are any. Currently, it doesn't seem like it. All right, I'll end the recording here. In the next episode, we will be creating maybe we will do the input layout wrapper since it should be fairly short. Otherwise, we will just create a standard input layout. Well, I'll ask if anyone has a preference. Yeah, but anyway, that's up in the next episode. We will probably do the input layout as well as the pipeline state in the same episode. So that's up next. Either way, we're working on the pipeline. All right. Hopefully, I'll see you in the next episode. And here on the live stream, I'll just do a short little break here where I upload the video file. Let's see. Oops. What did I do there? Okay. That was weird. And let's see, part 13. Let's see, and we will of course need to update the repo 13, creating a root signature. Okay, I'm getting close to a point where we might end up being a bit in a hurry if we are to need to do the whole thing today. Maybe I can do it. It would be nice to end the stream today in a state where we can do a few draw calls. Maybe not 3D draw calls, but maybe 2D draw calls. Then we can do a entire episode on the 3D stuff afterwards, and then people would have the basic tools to get going in terms of DirectX 12. Yeah. Remember, this is a tutorial series that you can influence if you ever feel like there's some topic that you would like to get any elaboration on or discussion of or implementation of, which is still at the quote-unquote beginner level. Let me know in the comments. I'll consider adding to this tutorial series if there's the interest for it. Let me just check that I updated the repo here. Github. Okay, that one. 1 minute ago. Okay. Let's see, application. Does it download the shaders? Yeah, it does. Great stuff. Great stuff. Okay. Well, let's continue. I'll start the recording here. Hi, and welcome to the next part of this tutorial series on creating your first DirectX 12 application in C++. In the last episode, we created the root signature, which is needed to create a pipeline. I also discussed a bit about what to do with the so-called input layout. I think we will hard code it into the pipeline since we will only be creating one pipeline. Since pipelines are something that you want several of, you would have to create separate root signatures and or maybe not, but you could create separate root signatures, and you could also create different input layouts. But since the pipeline wrapper is what binds these things together, we will get started on that in this episode. We did a wrapper for the root signature and everything worked out. Now we will create the wrapper for the pipeline state, as it's called. We will move it into our folder here, and we will do the usual namespace engine. And we will do the same here. This is also another interface of DirectX 12, so you know what we need to do by now. If not, you haven't really been watching anything I've done for the last 14 episodes or something. We will use the COM pointer ID 3D12 pipeline state, and we would like a possibility of creating a pipeline state that is default constructed, meaning that it doesn't need any state fill out. It can just be an empty class. Since we will be storing it on our renderer API, I think we should preface it with the YouTube API. We also want to store a root signature, which means that we need to include the root signature. These 12 root signature. And then we also need an array of shaders, because we will be creating a pipeline state that has 2 shaders. All right, and we will of course need a oh, did we forget in our last episode the release function? No, we actually did do the release function. Great stuff. We need a release function, and we need a destructor. We need a initialize method. And we created them. We want to call release. We want to call release on our root signature. We want to call release on our shaders whenever we release this. And we, of course, want to call reset on the pipeline state itself if it's set. Okay. Create pipeline state object. Maybe. Okay, we need a device, as per usual. If you remember from our first episode, the device is like the virtual context on which the DirectX 12 API actually operates on. So we basically need the device for most things that aren't simple command list recordings. Okay, let's see. A graphics pipeline state only takes a pipeline state description and somewhere to store it. Wow, that is easy. Think again. This is the pipeline state. It contains several descriptions that are expanded upon, and it's fairly long. So let's create a pipeline state description here. And let's call our method here. It will return an H result as per always. So we will ask our device here to create the pipeline state. Maybe it's graphics pipeline state. Was it graphics pipeline state? Yeah, well, it's also a graphics pipeline state, so that's great. And we want to store it in IID, PPV, args. And get the address of this pointer. We want to pass out an error. YouTube just complained about something. Okay, well, whatever. We will pass out an error. Improperly terminated macro. We probably need another parenthesis here. Well, okay, it doesn't complain, but it won't do as we expect. So we need to fill out some information in terms of our pipeline state objects. Let's just start at the top. I won't go over every detail, but as you can see here, we need a root signature. Okay, that's easy. We've created a wrapper for our root signature, and our root signature only takes a device. So we simply initialize our root signature. Right now, our root signature is predetermined. Let's see. The root signature object therefore we simply pass in our root signature .get. Great stuff. That was easy. We know that one. Okay. Then there's some structure here called shader bytecode. Well, it's a pointer to the shader bytecode and the bytecode length. And apparently we need to do it for something called VS. Wouldn't you know that it is actually short for vertex shader. So we need to set our vertex shader bytecode. Let's just agree that our first shader will be our vertex shader. We will initialize it with our path shaders, vertex shader HLSL, and we will pass it a shader type. Let's see, HLSL shader type of vertex shader. And we won't do that. We will actually initialize it here. But we initialize it, but we want the bytecode. Well, in our shader object, we have the bytecode. We can simply create an inline function that returns the bytecode. Get byte blob instead, because it's actually not the bytecode. The bytecode is part of this data structure, but it also contains the size, so therefore we will name it like that. You could argue that this is properly named as something else, but we don't care about that. Get the byte blob, and then we want the buffer pointer, and then of course we want to specify the length of the same thing. Therefore we duplicate this, get buffer size. Great stuff. All right, what do we need? We need a pixel shader. Oh my god. We need a pixel shader. We do not have created, we do not have a pixel shader. We will create one. Let's call this PS HLSL. We still want the entry point of main. We want a void function, and we don't want Visual Studio to try to compile this, so therefore we will exclude it from the project. Okay, let's set up our pixel shader here. We simply change the type here, and we got our pixel shader. Okay, pixel shader, shader bytecode, shaders. Oh, whoops, we need to set it in the second part of the array here. Shaders, get byte blob, get buffer pointer, and bytecode length. Get buffer size. Okay. Now we've told that this pipeline wants a vertex shader and a pixel shader. It doesn't need any of the other shaders, at least for our needs. We don't need a stream output buffer. So we can ignore that. We are not gonna pass out the information. We need a blend state description. Mm, mm, something about a multi-sampling technique. No, we don't need that. Let's see. Uh, the other thing does also sound a bit uninteresting for us. Hmm, well, let's see. The default values are these. We disable everything. These do not matter. Okay. So basically, if we fill out those, blend state, alpha to coverage enable, let's set that to false. Blend state, we will not be working with the blending at all. Therefore, we set it to false. Then the blend state, render target, the first one, blend enable, false. Blend state, render target, the first one, um, logic of enable, false. So we have basically, whoops, enable, disable blending on this pipeline. It will simply overwrite. This should be fine. I'm unsure whether it wants to render target right mask, but I think it's probably fine. Okay. After the blend description, we need a sample mask. We're not using sampling, so you might have guessed it. We do not use blending, but we want to sample everything, meaning that even though we're not doing, excuse me, sampling itself, we want to handle every pixel by doing nothing to it. So the sampling mask is actually specified in a bit field. We will set this to every bit, and then we will do sample description, which will be initialized as always as our standard values of a count of 1 and no quality, since we're not going to use it. Okay, rasterized seed. Oh, what is that? Okay, it relates to something about how we draw. It relates to something about how we draw stuff. So, rasterized state. Cull mode is the first one. No, fill mode. Fill mode. We will have the options of choosing solid or wireframe. We want to fill our objects with um, the wireframe, rather the solid fill mode, because we want solid objects. Let's do culling refers to which side of the triangle that we don't want to draw. If we do front face culling, front mode culling, uh, um, we only do back. If we do that, we only do front facing triangles. We might do none. Maybe we start out with none actually, and then you can play around with what you need in your um, setup here. Then we do the rasterized state front counterclockwise. This relates to the drawing order, meaning left or clockwise or counterclockwise. So this means that the front-facing part of the triangle is drawn counterclockwise. We will not use that for now. Yeah, let's see. Do we have any standard values? Yeah, we do. Our standard values are actually solid and back mode calling, so we will do that. Front is counterclockwise. Our depth bias, we don't care. Depth clip enable. Let's see. What does that do? Yeah, we don't mind setting the clip function to clip depth clip enable true. Okay, we will basically just follow the defaults. Multi-sample enable, no, no, no. And we will set this as a 0 initialized struct. So these will be automatically 0. These will be 0, 0. And conservative rasterization will be off. Okay. I think the rest is fine. Otherwise, we will probably get an error. Okay, that's the rasterized description state. The depth stencil state. Um, let's see. We will initialize that as 0 because we will not do depth testing before we have any actual 3D output. Okay. Now we're getting to the input layout, which is a let's input layout. That's the one that I wanted to do a wrapper around. Let's see. We will wait a bit with that. We want to set the primitive topology. We will be doing triangles. We will do the number of render targets, node mask 0. That will be later on. Number of render targets 1. And we will do our format for our render target RTV formats. We will only set the first one. And what's the standard value of that for us? We will get a DirectX 12 error if we do not specify the correct one. Let's see, maybe we just go with the standard one. No, okay. Format, didn't we actually, oh, we specified it already. We specified it in our swap chain, let's see. Okay, this is our format. Okay, we don't even need to guess. Okay. Then there's the depth stencil view format. The sample description, didn't we do that up here? Yeah, we did. Then we did the node mask. Cached pipeline state, we don't do that. Then we can do flags. We won't be doing any flags. And I think actually that is it, except this input layout. The input layout is always something a bit tricky. You have to specify a input layout description here. Let's see, what does it contain? The number of elements. Right now we do not have any, and we need some kind of array here. Okay. We need a series of a pointer to D3D12 input element description element. It's plural, and we simply initialize them. We can't initialize them as 0. Let's see, DirectX 12 input layout. Can we get a good example of a input layout? Nope. Okay, if we we can't access that. Okay, here's an input layout. It's a shader semantic, as they're called. It's a name inside the shader, the input assembler / vertex shader step that specifies what is this called in semantics in the HLSL shader language. We will, of course, discuss that in a future episode whenever we do our shading. And what is, let's look up the actual struct here. The as you can see here, this text explains it, the semantic, the input slots, different stuff here. The format of the data structure is also specified. I just look up this. So the semantic name, the semantic index, is that the same? Yeah. The format of the data structure, the input slot of the data structure, which is usually 0, I think. The way the aligned byte offset, meaning that where inside our input structure do we need to offset to access this data structure. Be mindful of overlapping data structures. And the classification here. Per vertex data or per instance data. If you do instance drawing, you need to use some kind of handling of instance data. But we specify information for each vertex in this pipeline, meaning that we will be using that input classification. Lastly, the data step rate in terms of how many instance or vertices per instance is actually used. So if you're using the same data for several vertices in terms of instance drawing or derivatives of that methodology, yeah, you would manipulate this factor here. We will only do a simple input. So if we basically copy this, there's no need to write out this if we can just use that. Let's see. And of course we want to do a oops, one here. And we do another encoding format. So this actually creates a data structure. Huh? Oh, it's the 12 one, but I don't think it changed. Maybe it's just like, let's see, DirectX 12. Whoops. There we go. And it's still the same information here. Okay. Yeah, we did the correct thing. Okay. The classification, let's see, blah, blah, blah. There we go. So we want this one. There we go. Let's just keep this like this. So we have the semantic called position. It's placed at semantic index 0, even though the example that we had earlier here is fine. Let's see. For the element, it's only needed where the elements have the same names, as you can see. You specify the format. Let's just return to that in a second. A number for the input assembler. And of course the bytes. So if we had two components, the aligned offset of the bytes would be passed in, I think, as this component here, and it would specify how large the structure is. This is a series of floating point numbers with 32 bits, 3 of them. So you can calculate how many bytes that is. It would be 12 bytes, meaning that the next semantic would have an offset of 12 bytes. So let's say that we want to use this input as our data. Maybe we actually want two kinds of input, a position and a color. So let's see, elements. Maybe we just want to point to the root. Yeah, okay. And we create another semantic here. Let's see, we create the color information. Let's see. And since semantics use captioned names, we do like, let's see, local variable is not initialized. So if I do something like this, let's see. Maybe we want double clamps here. Yeah. So our array elements here. Okay, back to this. There we go. There we go. So we would of course like a alpha value here. That is also 32 bits. As you might remember, the Second to last component specifies the byte offset, 3 times 32 bits is the same as 3 times 4 bytes, meaning that we have an offset of 12. So now we have created a pipeline that takes in information in the input assembler that has a position consisting of 3 floating point numbers with 32 bits and a color that has 4 floating point numbers with 32 bits. Great stuff. Okay, we're about to test out if our pipeline state here actually will be created correctly. Let's see. And we did specify the shaders and so forth. So let's test it. So we could simply delete this because now it's encapsulated inside our root signature. We don't want this. We want actually to store a pipeline here on our render API. And it's part of the whole setup here. Let's see, pipeline state, base pipeline. Okay. And then in our initialization step here, we want to create a initialize function where we pass in our device here. And let's see how this works. We have an error creating the pipeline state. Let's see if we get any information from DirectX in terms of creating it. We do get our debug information here. Pixel shader is not null. Okay. So actually this doesn't pertain to our pipeline itself, but it says that, well, you haven't provided us with a screen position in the rasterizing unit. What are you doing? We trusted you. We can't use this information. Okay, so this actually is helpful once you understand what it means. It means that we have some problem with our shader program. It said, the whole system said, fine, I'll create your pipeline, fine, I'll use those shaders, fine, I'll use that root signature. It's all fine and dandy, but you have enabled a rasterization unit. You expect to draw triangles, and the pixel shader is not null. So you need to pass me some basic information about where on the screen I should rasterize to, at least which pixels I should consider drawing. And I want you to translate that position before the rasterization unit. Therefore, this relates to something in our vertex shader, because if you may remember the graphics pipeline here, the rasterization unit is before our or rather, the vertex shader is before our rasterization unit, and it says that it wants it before the position is not provided by the last shader before the rasterization unit. Our last shader before the rasterization unit in this pipeline is our vertex shader. This is the power of the DirectX 12 debugging layer. If you have not implemented because you just wanted to skip ahead, you will never know what problems you have made for yourself in which areas of your program. So therefore, I highly recommend that you enable the debugging layer. Of course, if you're an expert and you know exactly what's going on every time, no matter what you're doing, don't enable the debug layer. Get a promotion wherever you are in this world. It sounds awesome, and I won't be able to do it myself. Let's just admit that. Anyway, so our vertex shader here needs to pass along something that the pipeline state can use, and I have a prior knowledge, so I happen to know what it expects to be input into the pixel shader and the rasterization shader, rasterization step. Um, uh, I'm not sure what your question means. And hello on Twitch. I'm doing a YouTube exclusive, so I'm not that good at responding right now. Let's see. But anyway, the thing that the DirectX 11 or rather 12 rasterization step and vertex a pixel shader step wants to have information about is the calculated screen position, and it's given in a system semantic for the shader programs. These are system semantics, and you can always look them up. But SV position is related to the pixel location. The documentation here is not really clear on what it means, but um, um, if you've worked with DirectX 12, you learn to realize that the S underscore S, sorry, the SV position is related to the screen space positioning. So it can also be used for some other things, depending on which shader it um, we're talking about. Okay, we will take a vertex shader output here and declare that. And we will pass out a float for position. And we will not initialize it, but we will give it the semantic SV position. I think we need to do like this. Yeah. So this is now supposed to return a output, but it doesn't right now. And we will create an output struct that is our struct that contains our position. If we compile this now, since we have a high or rather low tolerance for warnings, this will give us a warning and thereby a compilation error. So let's just initialize this. I'll go more in depth with shader language programming, but it's basically like any kind of programming language, and it's highly similar to C++ and C. So yeah, but now we've written a small vertex shader program that deliberately returns the SV position semantic to the next shader steps, which is our rasterization unit and then our pixel shader. So let's see if DirectX 12 now complains that we haven't provided the position. Well, it doesn't. Everything compiles, everything runs, we have no errors. So that was basically what it was trying to tell us. So once again, I advocate that you enable the debug layer. Let's no, I won't show you an example of where the debug layer won't provide any information in case you don't enable it, uh, because yeah, that's kind of pointless. Anyway, okay, I'll try to do the last steps of this episode rather quickly because I have to go in a short while. Let me just check. Yeah, I have to go in a short while. So let's create a data structure that actually mirrors our pipeline state, because we told the pipeline state that we expect this input for information. The problem is that um, well, I don't think that Microsoft has done any particular applications, but WPF is rendered in DirectX 9 or something, maybe even DirectX 10. So that's a basic example of an application that runs DirectX without being a game. So, but yeah, I won't create applications that are not games, because DirectX 12 is um, really game focused. I think there might be easier APIs to do applications that are not game related, at least. You could do 3D drawing models, but it will be basically the same as games, renderers, graphics editing programs, and so forth. Anyway, our input description here is related to these data structures here, and actually our uh, vertex shader here will have a input that is passed along from the inputs um, merger input state here. So we know that it will get the float 3 data and the float 4 data when we the input assembler passes its data along. So we can create a variable here in the struct for our input that is called position, and we named it position. So therefore we couple the variable with our semantic. We also name this color, so we will give it our color. And remember, we specified the semantic here, so they are linked not only in terms of memory layout but also in terms of the semantic. The shader expects this because we created a pipeline that is defined this way. Okay, as per any other method definition, we simply tell our program here, well, we get an input that has this structure here. Now we can simply swap our position. Maybe we want a float 3 as instead for our SV position, and therefore we simply copy our position here from our input. In the future we will do calculations on it. Maybe we want to pass the color along as well, so therefore we simply create a field that allows us to store our color. We then copy this data structure here inside our pixel shader, because we know that this pixel shader information will be passed in from the vertex shader output. And it will contain these semantics, and it will a pixel shader will also return a pixel color with an alpha value. So therefore, right now we will just return the color white. Now we will actually use the pixel shader input here and return the input dot color. Since the SV position actually determines the pixel on the screen in terms of positioning, the color can just be passed along and it will draw whatever color to that pixel on the screen. The vertex shader translates the information in terms of through the rasterization unit, of course, into pixel coordinates. But yeah, let's see if everything compiles. Okay, we have a problem. What's our problem? Shader compilation error. Not all elements. Okay, we actually need a float 4. My bad. And we can do like this. Let's see. Yeah, so let's see, does that work? Okay, now we only have one error. And lastly, our return value here of the pixel shader is not correct. It warns us that the semantic is missing for this return value. Well, what is the return value? Or rather, what is the semantic for that return value? And we can again look into our system here. System variables, target, the output value that will be stored in a render target. The index indicates which of the 8 possibly bound render targets to write to. The value is available to all shaders. So we simply want our output semantic here to be bound to the target, and you don't need to specify the render target. Let's do naming here. That is as our convention, because it will just use the default one. Okay, what's our next problem? Our input signature parameter must be float 32 and must be XYCW. Okay, so it quickly knew that we weren't returning a float 4 instead as the appropriate semantic. Okay. Now we basically have a shader program that passes along the screen positioning and the color for our vertices. Great stuff. I think I won't be able to make it in terms of doing the actual draw calls. We are really close in terms of doing the draw calls. We actually just need to upload and bind the stuff together, and then we can do a draw call. But I think this episode has been fairly long, and yeah, since it's a small but relevant topic that I don't need to rush through, I will end the episode here. So we started doing shader programming without me even giving an introduction to that. It's not a real programming tutorial, so you might already know how to program shaders. Anyway, at least I hope I explained parts of where the pipeline state and the shader programming languages are bound together, and why the application fails whenever the programming shader programs doesn't fit the defined pipeline. It's because the shaders, the pipeline, the root signature are all parts of what takes data at the input assembler and outputs something to a render target and eventually to our screen. So they are intricately wound, and you need all objects and you need them to fit together, so to speak. All right, I think that is it for this episode here. Are there any questions? Otherwise, I'll end this episode. Well, it doesn't seem like it. Excuse me. Okay, I think we got a really long way. We're about to do our first draw calls in our next episode. There's literally only a few lines of code left, and we of course need to upload some data, but we will do that fairly quickly. Yeah, that was progress. If you have interest in me doing the actual 3D rendering in DirectX 12, let me know either in the comments or during the next stream/episode. If you have any wishes for future topics that this tutorial series should branch out into, let me know. For me, this takes time out of me working on my own project, so therefore I will only be doing certain tutorial/episodes in case there are high demand for it. I'll of course finish this up so that there are no loose ends and you can at least do a bit of 3D rendering. Yeah, but I won't be doing any advanced or intermediate or even beyond beginner topics without a large enough interest, since yeah, I spend a lot of time on doing these episodes. Anyway, if you found this helpful, inspirational, or useful in any kind of way, maybe entertaining, even though I only make bad jokes, feel free to comment, like, or subscribe, or even support the channel. The GitHub repo will be updated, and you can always use the commit history to go back to earlier episodes and use different builds of this setup. Yeah. All right. Thanks for tuning in, either during the live stream or in the future. Stay well and have fun. Bye bye. And here on the stream, I'll just be winding down while I upload that episode. Let's see. We have episode number 14. Let's see. Okay, let me do the commit here. Let's see. And did we get it all up on the repo? Yeah, we did. And it also uploaded the shaders. Great stuff. All right. I'll be shutting off the stream. Thanks for tuning in. Hopefully I'll see you in the future.